I've just got half an hour before going to bridge, so I'll try to work on problem 6a. Last time when I was going to tennis and just had, was it like 1 hour, I thought I could solve a problem. I did okay on the math, but then when I had to play tennis, I just couldn't see the ball. And I concluded afterwards that working on a screen with a computer ruined my eyesight for some time, but I don't need that for playing bridge. Well, let's get on with the problem. First, when I saw this, I thought I had done that while studying the section, but then I realized there's n to the a and a. So let's get on with it. And then we write this as a sum of x to nth to like I. And it converges absolutely when x is numerically smaller than 1. So we'll just exchange order of summation. And then it's I plus 1. So instead we let I and n both go from 1 to infinity. And collect terms where ni equals, do we? Well, we've got to. Or do we? Yes. So we define a new variable k as the product, and then when we have the product we let n sum over all the divisors. That's simple, and then we sum over n to get sigma a of n x to the kth. That's all divisors of k, of course. So we sum over all the divisors of k here, so we get sigma a of k, and that was what we should show. A is equivalent to 1 modulo 4, so a plus 1 is equivalent to 2 modulo 4. And we must use the proposition 8 again. Otherwise, not taking in the left. We'll just do that. 1/2 v of I of f plus, and f is one of the modular forms. I don't want to write all that. 1/3 of omega plus the sum of the order of zeros minus the order of poles of other points, including infinity, equals k halves. Now k is equivalent to 2 modulo 4. Meaning we can divide by 2 and no more. So it gives like, if it's 2 itself, then it's 1/6. If it's 6, then it's 1/2. And if it's 10, then it's 5/6. These two guys, they can only be fulfilled if we have zeros at the imaginary unit. But this one, that's, that's 1/2 minus a third. So that would require a pole. Couldn't we get 1/6 another way? I don't see we can do that. Well, if it's like 14, then it's 1 plus 1/6. Oh yeah, and then we, what? I actually didn't study the proposition or k equals 14 very well, because I should have known what are the zeros of E14. How can we, from 1/2 and 1/3, take like 7/6? I'll just pause the video and check that, because I really don't understand what's going on here. Well, it is in the proof of proposition 9 that we can have a double root at 1, what does it say? A double root at omega and a single root here. So 1/2 plus 2/3, right, 7/6. All right. So in all the cases, this one as well. Oopsie. We will have a root, in this case a double root, at I, and therefore this holds. So that was an application of proposition 8. I was just not able to do the technical details. All right. Prove this guy, or radio. I'll write it to make sure that I copy the content. E to 2 pi up here. And how about the definition of the Bernoulli numbers? Well, well. Ah. No. I thought I could divide by e to 2 pi nth. Oh, but that is exactly what we've got. So all we have to do is to set x equal to e to minus 2 pi, and then apply this guy. I'll just write it up to check that we do have the right. We are summing from n equals 1 to infinity, n to a, x to nth divided by 1 minus x to nth. That's exactly what we've got. Well, we know the result. Now what? This, of course, is connected with the some of the formulas in the book, particularly what will it be? E6, E10, etc. You know what? I'll just write up the formula because I can't do it in my head. That's of course k minus 1 of n x to n. X to n. It was q to n. Yes, of course it's q to n. Z. Oh, it's already e to minus 2 pi. I'll just write q to n. So we isolate this. But then it's a function of z. What happened to that? Oh, I didn't finish this. We have to finish this first. Sum here equals e to minus 2 pi. That's the value we get from if z is equal to the imaginary unit, then q equals e to 2 pi z equals e to minus 2 pi. Now I can see the way through, and I have another 10 minutes to go. So this equals 1 minus EA of I times BK divided by 2K. Whereas the K, it should be A plus 1. And first we showed that the value at the imaginary unit vanishes, and I should have taken that as a hint that we needed to get back to this. I missed that. There we go. As for the examples, I must admit that I still feel a bit alienated to the Bernoulli numbers, so I wanted to see them again and then compute this fraction that occurs as the result. And these are nice fractions, but then it becomes quite complicated as they increase. I believe that was the next problem.